This is the third and last slide set for the reinforced concrete foundation design. And this slide set is going to be mainly about the reinforced concrete design itself. It's not about sizing of the footing. The previous slide set, we went through sizing of the footing itself, which means length by width, to determine the contact area between the concrete footing and between the soil. In the slide set, we're going to have an example that we need to go through and see how we can design the thickness and how to design the reinforcing within the footing. This footing is exposed to vertical load. The vertical load is equal to 600 kips and the service moment of 720 kPa. This is the same example that we have done already in the previous slide set. The loads given here, they are service loads. It doesn't say if there's going to be dead load or live load. Therefore, I'm going to consider them to be dead load only. This is going to be kind of very standard thing that we do if you don't really know if this is going to be dead load or live load. You just consider it to be dead load. So if you like to find out the factored loads, what you need to do is to have your load factor of 1.4 multiplied by this given vertical load or rotational load, which is the service moment. The column size is given as 16 by 24. Concrete strength is 4000 psi, and the steel yield strength is going to be 60 ksi. The footing thickness is going to be 30 inches. Two items that you need to determine here. Number one, reinforcing of the footing in the longitudinal direction. Number two, reinforcing the footing in the transverse direction. We were able to determine the stress distribution under service loads previous slide set. Due to the vertical load, I have a stress of F sub P is going to be equal to 5 kip per square foot. Due to the moment, I'm going to have here a stress which is equal to M over S is going to be equal to 3 ksf. For detailed calculations of F sub P and F sub M, you need to go back to the previous slide set. Based on this stress distribution, on the right hand side, we're going to have the moment pushing the footing down, and also the vertical load is also pushing the footing down. Therefore, the stress on the right hand side, which is 0.1, is going to be additive, is going to be equal to 8 ksf. On the left hand side, the moment is causing this footing to lift up. At the same time, I have the vertical stress, the vertical load coming to push the footing down. Difference is going to be equals to 2 ksf. It's going to be 5 minus 3. Therefore, the right hand side stress is going to be 8 ksf. The left hand side stress is going to be equal to 2 ksf. This is here due to service stresses. And with that, you should be able to size the footing and do exactly what we have done the previous slide set. Now I need to determine the steel within this footing. Now the reinforcing steel is going to be at the bottom. The reason is because the stress is going to be pushing this pad up from both sides. However, at the footing column, you're going to see here that you have this here tension is going to be at the bottom of the footing, top of the footing is going to be exposed to compression. Now, in order for us to design the footing reinforcing, we need to have factored loads. And also we need to have factored stresses. And how do you do here the factored stresses? What you need to do is to take this stresses multiplied by 1.4. Reason is because if I assume that the vertical loads and the moment was dead load, therefore to factor it, I'm going to multiply it by 1.4. Therefore, the right hand side, the stress is going to be 8 times 1.4. With that, I have 11.2 ksf. On the left hand side, this is going to be equal to 2 ksf. The distance x is going to be equals to total length of the footing, subtracting the column length divided by 2. And actually, this is going to be the cantilever length. Now let's look here at the stress distribution on the right hand side. Someone's going to ask here, why don't we take the left hand side when it comes to the moment calculation or the stress calculation? It is very obvious here that I have more stress on the right hand side, which means I'm going to have here larger force acting on the footing cantilever side, on the right side, compared to the left side. Now looking at the stress, I have here trapezoidal distribution. If you cut the section right at the face of the column, and I'm showing here a dashed line, the right side maximum stress is 11.2 ksf, the left side is 2.8 ksf. By interpolation, you should be easily finding the stress at the face of the column, which is 7.7 ksf. The right hand side point is called point 1, so the stress right there is going to be F sub 1, because the stress at point 1 is going to be sub U, because you have ultimate stress or factored. On the left hand side is going to be F sub 2U. Reason that we are using 2 because it's going to be 0.2, sub U because it's going to be ultimate stress. The 7.7, which is right at the face of support, I'm going to call this F sub 3U. For this trapezoidal distribution, I can divide it into two forces. I'm going to have here F sub 1 and F sub 2. F sub 1 is going to be located at the moment arm from the face of the support, which is x1, while F sub 2 is going to be located at distance of x2. Now this x1 is going to be for this rectangle, the rectangular stress distribution, which means x1 is going to be equal to the value of x cantilever length divided by 2. It's going to be right in the middle of this rectangle, while x sub 2 is going to be equal to 2/3 of the cantilever length x, because F sub 2 is located at 1/3 of this triangular shape from the right hand side. So now the calculation that I need to do is going to be find out the force F1 and finding out x1 and also finding out F2 and x2. Total moment at face of support is going to be equal to what? Now I have two forces, two moment arms. If you take the moment here at face of support, it's going to be equal to F1 times x1 plus F2 times x2. Now x is going to be the critical section for the moment, which means the cantilever length. Now I have here total of 12 feet, which means 1/2 of the footing is going to be 6 feet. Column length is 24 inches. This is like 2 feet. 2 feet means from the center of the column or the middle of the footing to the face of the column is going to be a foot. So I have here 6 minus 1 is going to be 5 feet. So cantilever length is going to be equals to 5 feet. Therefore, x1, the distance from f1 to the face of support, is going to be equal to 2.5 feet. Now here's calculation for the stress at face of support. This here by interpolation. I'll let you here do this in an easy way, in the way that you like. You need to use here the tricks and the skills that you have learned to do interpolation to find out the stress at face of support. Now the first rectangle, when it comes to the stresses, is going to be equal to 7.7. This is the stress, which is the height of this rectangle, times 5 feet, which is the length of the cantilever, multiplied by 10 feet, which is the width of the footing in the perpendicular direction to the screen. For the triangular shape, distribution of the stresses is going to be equal to the height of this triangle, which is 11.2 maximum stress, subtracting the 7.7 for the rectangle. Multiply this by 5 feet, which is the cantilever length. Divide this by 2 for the area of triangle. Multiply again by the width of the footing, the 10 feet. With that, I have 87.5 kips. Now the x1 distance is going to be equal to 2.5 feet. 5 divided by 2. The x2 distance is going to be equal to what? 2/3 of this 5 feet. Now let's look here at the final equation. It says M sub U, this is going to be the moment acting on the concrete section of the footing, is going to be equal to x1 F1 plus x2 F2. That I have 1254.17 cubic foot. Now I have my equation for the moment. Vmn is going to be equal to the standard equation that I have from the ACI. The tension force AS times Fy times D minus A over 2. I don't know exactly how much reinforcing I need. So I need to assume that D minus A over 2 is going to be equal to 0.9 times D. Just an assumption. As I said in the past, this can range between 85% of D to maybe 95% of D. I'm talking here about D minus A over 2, the moment arm for the AS times F sub Y. Now in this equation here, I need to set M sub U to be the same as Vmn. M sub U is at 1254.17. Again, say it's going to be equal to Vmn, and based on this, I need to determine here A sub S required. This is going to be an approximate method of doing it, and with that I have nearly 11.9 square inches. With this 11.9, now I can try here 15 number 8. Why 15 number 8? Number 8, it has a cross-section area of 0.79. 15 bars of these is going to be 11.85 square inches, which is roughly equals to 11.91. It's not really greater, it's going to be very close to it. And the amount of tension force is going to be equal to this actual AS multiplied by F sub Y. I have here 711 kips. Now you can determine here compression block depth from the standard equation that we have been using. And what you have here is going to be 1.74. Now once you have the A, and of course you have the concrete, you can confirm here the phi factor by doing this C over D. This is an exercise that you need to do it. I'm not going to be going here through it, but I'm sure that you guys know how to do it. Now after this, I can figure out Vman, which is the ultimate capacity here if you like, or actually I'm going to code here the capacity of the section, the strength of the section and flexure. Be sure that usually this M sub U and Vmin is going to be reported as in kip foot. You cannot have it as in pound inch. You need to report this as going to be in kip foot. Vmin, the strength to be 1340 kip foot, while the demand is 1254. This is actually a very good design. How about transverse direction? You're going to see critical section the other direction. You have the total width of the footing is going to be 10 feet. And the column is equal to 16 inches. So I'm going to be taking the cantilever length is going to be 4.33 feet. Now the factor of stress, I have 11.2 kSF for the maximum stress. The smallest stress here on the other side is going to be equal to 2.8 kSF. With that, I should be able to figure out the total force. Now the force is going to be located at one half of the distance of the cantilever length, which is a 4.33. The amount of stress that you have there is going to be trapezoidal stress distribution, and with that I should be able to figure out the total force. In the previous slide, I considered the entire width of the footing when I calculated out the moment at the face of the column for the transverse direction. Now in this example here, I'm going to be taking only the side of the footing that has bigger stresses. Means I'm going to be taking here the stress from the very high stress, the 11.2, all the way to the center of the footing, which is 7 kSF. So now here we go. The trapezoidal here is going to be 11.2 plus 7 divided by 2 times the cantilever length times 6 feet instead of 12 feet. Now here's the force. Moment is going to be exactly the same way that we have done the previous slide set. previous slide. Excuse me for that. Now this moment calculated out is going to be almost 512 foot. Is going to be applied on a width of 6 feet of the footing. Now compare this moment here with the previous moment calculated in the previous slide. It's completely different because what I have done here, I have considered here the stress that starts at 7 ksf all the way to 11.2 ksf, and instead of having this uniform stress throughout the entire width of the footing, which is going to be 7 ksf. After you do the moment here, what you need to do is to figure out the amount of reinforcing. So very similar to the longitudinal direction of the foundation, now we can do the transverse direction of the footing when it comes to the rebars. Now you got to be careful about the depth of the footing when it comes to the transverse direction. Location here of the rebars is going to be above the rebars in the longitudinal direction, meaning now the depth from the top of the footing to the bottom of the tension rebars is going to be equal to 30 inches. You subtract here 3 inches for the cover, you subtract 1 inch for the rebar size, and then you subtract additional half an inch for the half, which means the radius of the top rebars. I'm not saying top is going to be at the top of the footing. It's going to be the top layer of the rebars, which is in the transverse direction. Now the required here, AS required, is going to be equal to the moment demand. And then, of course, as you consider here, 90% of the depth to be the effective D minus A over 2. Now you need here 4.95 square inches. You will provide 7 rebars of number 8. And this is going to be applied here for a width of 6 feet, which means for the entire footing of 12 feet, you're going to have 14 rebars. Here's the tension that you have in the bottom rebars. Here is the A value, concrete block depth, and with that you have Feman of 617.77 kfoot. Now here's the footing. As you see here, longitudinal reinforcing is going to be below the transverse reinforcement. I have here 15 number 8. Transverse reinforcement is going to be 14 number 8. Here's an elevation. This is the way that we showed in the elevation, and this is the way that he showed on the plan.